Continuing with our unit, long ago and far away, let's talk more about how we measure sizes, distances, and brightnesses of things we see in the sky. Following is an outline of the topics that will be covered in this lecture, along with the units where you can find these topics in your textbook. We will begin by reviewing the basics of our solar system, the scale of the universe, scientific notation and units. We will talk about the scientific method and the sizes of the Earth, Moon, and Sun. Then we will go on to a historic account of the beginnings of modern astronomy, which I like to call the BKG unit for Brahe, Kepler, and Galileo, the three most important founders of modern astronomy. And then we will end with a unit 54, 55, and 26 coverage of the luminosities of the stars and special relativity. So to begin with, let's take a look at our planetary neighborhood. This is our home planet, the Earth. Some facts about it appear on this slide. In kilograms, it's almost absurd to write all the place values needed to express the actual mass of the Earth. Instead, scientists use scientific notation for large numbers such as this. The 5.97 times 10 to the 27 kilograms that you see here means that the decimal point really goes 27 places to the right of where it is now. It's a more compact way of writing this number. As you know, the Moon orbits the Earth. We call objects such as this a satellite. The Moon is about a quarter of the diameter of the Earth. It is very cold and airless, consisting of only a very tiny, diffuse atmosphere. One thing you notice when you look at the Moon are all of its craters. It's a wonder if the Moon has been bombarded so much by meteors, resulting in such craters, why we don't see as many on Earth. Can you think about why that might be? Well, the Earth is subject to weather patterns that are non-existent on the Moon. Erosion, plate tectonics, and other factors do a lot to erase the damage done by bombarded meteors. But make no mistake, the Earth has been bombarded as many times as the Moon. When we look at our planet, the planets in our solar system, and the dwarf planets in our solar system, we notice that they are not all the same. Some are rocky, some are gaseous, some have rings, and they come in different colors as well. In this course, we will start to learn why they appear the way they do, why they are so different, and what different things they are consistent of. All of the planets, dwarf planets, comets, and asteroids orbit the Sun in our solar system. The Sun is about a middle-aged star, having lived through about half of its lifetime. Its total lifespan will be about 10 billion years, and we are now at about the 4 billion year point. In addition to planets and dwarf planets, we also have asteroids, comets, and other such objects that orbit the Sun. Some things follow highly elliptical paths, and other things look a little bit more circular, although nothing is a perfect circle. When measuring the distances within our solar system of one object to another, it's useful to use something called the astronomical unit. Instead of talking about millions of kilometers, it's easier to redefine a unit which is larger. Larger so that we result in smaller numbers. And what that unit is the astronomical unit. 1 astronomical unit is about the average distance between the Earth and the Sun, or equal to 150 million kilometers. This allows smaller numbers to be expressed in the distances in our solar system. For example, the distance from the Sun to the Earth is 1 AU. The distance from the Earth to Mars is about 1.5 AU. The distance from the Earth to Saturn is about 10 AU. Let's look beyond the solar system now. The solar system consists of planets that orbit a star called the Sun, which is one of only billions of stars in the Milky Way galaxy. Where do all these stars come from and how do they live their lives? These are questions that we will answer through the course of this class. Even the AU, or the astronomical unit, is insufficient to try to express the distances within the Milky Way. Instead, we need something even larger, which is why we turn to the unit called the light year. The light year is the distance that light can travel in 1 year. We think of light as being instantaneous, but it actually has a finite speed it cannot exceed. It takes time for light to get from one point in the universe to another. And in fact, in 1 year, light can travel 10 trillion kilometers. So we call that distance a light year. Our closest neighbor in the stellar neighborhood is Proxima Centauri, which is about 4 light years away, meaning that the light that we see left Proxima Centauri in the Alpha Centauri system about 4 years ago. As we saw in the last lecture, the universe consists of clusters of galaxies, which are clumpy with voids in between, and they look like filament-like structures if we zoom out. Let's talk more about the astronomical numbers, such as the astronomical unit and light years. Some other units that we use in astronomy are units that hail from the metric system. These are not as intuitive to most Americans, so you see some conversions here to give you an idea of how large they are. A kilometer is a little bit more than half of a mile. A kilogram is a little over 2 pounds. And a change of 1 degree Celsius amounts to almost a change of 2 degrees Fahrenheit. Scientific notation is a convenient way and a more compact way to write very large or very small numbers. Instead of writing out all the zeros preceding or following a number, we instead write the number followed by a 10 to a certain power, which will tell us how many decimal places over the decimal point ought to be. If you see a negative exponent, that means that the decimal point should really be moved to the left. If you see a positive power, this means the decimal point should really be moved to the right. For example, a kilometer could be expressed as 1,000 meters, or 1 times 10 to the 3 meters. On the other hand, a millimeter could be expressed as 0.001 meters, or 1 times 10 to the negative 3 meters. As we mentioned earlier, a light year is the distance it takes light to travel in 1 year. An even larger unit is something called the parsec, which comes from a contraction of the terms parallax second. It is equal to over 3 light years. Let's take a look at the foundations of astronomy. In order to discuss astronomy as a science, we need to understand what is meant by the scientific method. This is a source of great confusion in popular understandings. What we do with the scientific method is that we start with a hypothesis. Hypothesis has to be a testable idea of how something in nature works. It must be testable because we want to subject the hypothesis to testing or experimentation. If the test fails even once, then the hypothesis needs to be modified or abandoned. However, if the hypothesis is confirmed by testing repeatedly over many years by many independent scientists, then the hypothesis stands a chance of becoming elevated to the status of a theory or a law. Please understand that theories and laws are equivalent factual descriptions of nature. When we say scientific theory, we do not mean an educated guess. We simply mean that it is as factual understanding of nature as we can prove at this time, based on many years of testing of hypothesis. The only difference between a theory and a law is that a law can be expressed as a mathematical equation. For example, Newton's second law says that the force of an object equals its mass times its acceleration. F equals ma. That is an example of a law. Theories, on the other hand, need to be described with words. They're simply not as concise as a law. Therefore, there is no simple mathematical expression that one can use to summarize a theory. However, rest assured that a theory is considered a factual description of nature. So when somebody says it's just a theory, what we mean when we are scientists is that would be the same as saying it's just a fact. What people mean colloquially when they say theory is something closer to a hypothesis or an educated guess. We also need to understand what matter is made of in order to understand what's out there in space. If we look to the very small instead of the very large, we see that atoms and molecules are composed of tiny subatomic particles. In between those subatomic particles is lots of empty space. And the smallest particles are particles which make up protons and neutrons. They are known as quarks. Moving on, let's discuss the geometry of the Earth, Moon, and Sun. How did ancient people have any idea that we were standing on a sphere when we were standing on the Earth? It turns out that they did have an idea. Aristotle, in fact, was able to conclude that the Earth must be a sphere based on the fact that when a lunar eclipse took place, the shadow of the Earth on the Moon followed a curved path. He also noted that stars that are visible in the northern hemisphere are not always the same as stars visible in the southern hemisphere, and this could only be the case if the Earth was in fact a sphere. Arcturus, who lived around 300 BC, was able to go a little bit farther and estimate the size of the Moon in relation to the size of the Earth. He did this based on the shadow that the Earth cast during an eclipse, and he estimated that the moon was about a third of the size of the Earth. This was a fairly accurate estimate. He was also able to determine an estimate of how far the moon was away from the Earth based on how long it took to pass through the Earth's shadow during the eclipse. Again, his estimate was fairly close. It's amazing to think about ancient astronomers being able to come up with such estimates with no tools with which to gauge these things. Arcturus also tried to make an estimate of the distance to the Sun. This was very difficult to do because the angle that he was looking at was hard to measure precisely. So his estimate in this particular distance was not very close. But it showed that we could think about the geometry of things and deduce a little bit about what's going on with the distance and sizes of the Earth, Moon, and Sun. Arcturus also postulated that the Earth goes around the Sun and not vice versa. This was not a popular idea at the time, and most people rejected this idea, even though it was correct. They pointed towards the fact that if indeed the Earth went around the Sun, then we ought to see something called a parallax, which means that if we were looking at a close-by star in July compared to very distant stars in the background, it should appear in a different location due to geometry than where it ought to appear in January, as depicted by the diagram above. It turns out that the reason this parallax could not be detected is because the angle was in fact too small to measure with the naked eye. We needed telescopes in order to measure it, but this parallax does exist. It was just indiscernible in Arcturus' time. Eratosthenes wanted to know about how big the Earth was. He noticed that on the summer solstice, the longest day of the year, the sun was directly overhead in a town called Syene, but that it was not overhead in his hometown of Alexandria. In fact, it made an angle of 7 degrees at high noon. From that information, he was able to calculate geometrically that the diameter of the Earth ought to be about 13,000 kilometers, which is almost exactly correct. The only tool he used to measure this was a stick to determine the angle of the sun in Alexandria. When we look at distant objects, we often talk about their angular size. This is easier to determine when we are looking at distant objects than the actual size of the object itself. In other words, the moon appears to take up about 0.5 degrees when we look at it from the Earth. Knowing that information, we can geometrically determine the actual diameter if we know the distance to the object. The particulars of this mathematical equation you do not need to really know. But the point is that it can be calculated based on principles of a circle. Let's take a look at some more history. We've talked about ancient history. Let's move forward in time. If we go to the 16th century, we can talk about the life of Tycho Brahe. He was able to use instruments to very accurately measure the position of planets with his naked eye. And he kept records of these planets' position in the sky. His observations were crucial to deducing how planets orbit the sun. Although Brahe believed that the sun orbits around the Earth and not vice versa, his observations were the turning point in understanding how our solar system works. Johannes Kepler was the man who used Tycho Brahe's observations to figure these things out. Based on Tycho Brahe's data, he was able to conclude that the planets actually revolved around the sun, and that despite him greatly wishing that they moved in circles around the sun, it turned out that the only way to explain the data was by using ellipses. Kepler believed that the circle was a perfect shape, and that the perfect heavens ought to obey a circle shape for their orbit. However, it turned out that only the ellipse could explain the motion of the planets. Kepler's devotion to the data, despite his personal feelings, is what makes him such a great scientist. The size of the ellipse is such that from far away it would be difficult to discern that they were not circles, but in fact they are slightly oval in shape. Kepler came up with 3 laws to describe planetary motion. His first law is simply that planets move in an ellipse, with the sun at one focus, instead of the center, like you would have with a circle. In other words, the sun is slightly off-center. Kepler's second law is that while orbiting, planets sweep out equal areas in equal time intervals. For example, in the diagram you see here, the fat wedge of area on the left-hand side, representing 2 months of time, is fat in size, but the area is the same as the thinner wedge on the right, which also represents 2 months of time. This is because on the right, that shape is elongated. So it's not fat and squat, but the area is the same as the one on the left. What this means is that planets move faster when they are closer to the sun and slower when they are farther away. So since the sun is offset from the center, this means that during some point in its orbit, a planet approaches the sun a little more closely than during other points of its orbit. Just to warn you though, in case you think that this is the reason we have seasons on Earth, this has nothing to do with the seasons on Earth. In fact, we are actually closer to the sun during the winter in the northern hemisphere than we are during the summer. We will discuss seasons more in depth in the future. Kepler's third law was a relationship between how long it took a planet to orbit the sun and how far away from the sun it was. A semi-major axis of an ellipse can be thought of as an average distance of the planet to the sun. If we take that average distance to the third power in astronomical units, then that should equal the time it takes the planet to orbit in years squared. Another important astronomer who lived in the 16th and early 17th century was Galileo. Galileo did not invent the telescope, but he was one of the first to use it to observe the heavens. He found a lot of interesting facts. People thought that the sun was a perfect sphere, but he noticed that the sun actually had spots on it. He saw craters on the moon, and he discovered that Jupiter actually had 4 moons which orbited it. This was important because people at the time believed that everything should orbit the Earth. Galileo showed that things orbited other things from the Earth. The 4 moons of Jupiter went around Jupiter, not the Earth. He also, most importantly, discovered the phases of Venus. This was important because the only way to explain these is if Venus orbited the Sun. Let's move on to Unit 54, Surveying the Stars. We're going to briefly touch on some of the geometries that are used in determining distances to various objects in the heavens. Triangulation is one way we can figure out how far away things are. We can use triangulation for near objects, where it's possible to measure the angles depicted in the diagram here. It's possible, for example, to come up with an estimate of the distance to the moon based on triangulation. This distance has been verified by the fact that Apollo astronauts who visited the moon placed mirrors there, allowing us to send a laser pulse to the moon and bounce it back. Knowing the speed of light then allowed us to determine the distance to the moon very accurately. Parallax is another way we can gauge the distance to objects. If you hold your thumb out in front of you with your arm extended and close one eye, covering up a distant object, then if you switch eyes, you will see that your thumb is no longer covering up the same thing. You can think of one of your eyes as representing one point in the Earth's orbit, and the other of your eyes representing the other point in the Earth's orbit, perhaps July and January. Things that appear in the distance should look different to things in the foreground during different parts of the year. This again was the reason that people did not believe Arcturus when he said that the Earth revolved around the Sun, because they were unable to detect any kind of parallax. But with the aid of telescopes, we can detect parallax for very close stars compared to very distant stars. If you look at the 2 small images on the right-hand side, you see an example of a foreground star in July compared to where it might be in January. This tells us that that star is much closer than the distant stars in the background. Using trigonometry then, we can figure out exactly how far away that particular star is. We don't need to go through the math in detail, but just a vague understanding of how this works is important. Of course, parallax can only be used for the most close stars. And even the stars themselves are actually in motion. If you could fast forward in time, the Big Dipper will not look the same over time. That is because the stars that make up this constellation are in motion. And over time, their shapes will change. The constellation's shape will change due to the motion of the stars in the constellation. They are not all going the same speeds or the same direction. Let's talk about the luminosity of stars. In other words, how much light do they give off? Looks can be deceiving. This image here, if you knew no better, you might think that Comet Halley gave off about as much light as Alpha Centauri or Beta Centauri, because it appears to be about as bright as those stars in this image. But the thing is, we know that Comet Halley is actually much closer to us than the Centauri system. So how bright something appears to us is related not only to how much light it gives off, but also how far away it is. The light has to spread out over distance. In fact, it does so in a very predictable way. In this cartoon, The center sphere, small sphere, represents a star. The light the star gives off spreads out in a larger sphere surrounding it. If you place this telescope at distance d away and another telescope at distance 3 away, then you would find that the brightness in the farther away telescope is not a third of the brightness of the closer telescope, but it's actually the square of that, 3 squared, or 1/9 as bright as the star is for the closer telescope. So as light spreads out, the distance squared is how much the light gets reduced by. We call this an example of an inverse square law. Light obeys this law, as does gravity and other laws of nature. In this image, you see street lamps. All the street lamps have the same wattage, giving off the same amount of light. But the one in the upper left-hand corner is much closer to you than the ones more distant. So the distances between them is related not exactly to the brightness, but the brightness is related to the distance squared away. To put that in mathematical terms, if B represents brightness, L represents luminosity, or the amount of light which is output, and D represents the distance, then the brightness is equal to the amount of light put out divided by 4 pi times the distance squared.